To start our discussion on this lesson, let's define some terms. When we say condensed matter, this is solid or liquid, which is a combination of atoms to form molecules or more extended structures. Condensed matter physics, on the other hand, is a branch of physics that deals with the physical properties of condensed phases of matter. Condensed matter physicists seek to understand the behavior of these phases by using physical laws, near quantum mechanics, electromagnetism, and statistical physics. In this lesson, we're just going to give you some brief overview about your condensed matter physics, and then your semiconductor materials, and some examples of your semiconductor materials. This is a question. What is the difference between materials like glass or butter and solids like ice or copper? Ice and copper are crystalline solids, meaning they have atoms that have long-range order, a recurring pattern of atomic positions that extends over many atoms. Glass and butter, on the other hand, are amorphous solids, which have short-range order correlations between their neighboring atoms. So that's basically the difference between your glass or butter and solids like ice or copper. Ice and copper are crystalline solids, while glass and butter are amorphous solids. Now, when we say crystalline solids, they basically have this crystal structure. And when we say crystal structure, this means a periodic arrangement of atoms or ions over large atomic distances. Just take note of this keyword, you have your periodic arrangement. And your crystal structure leads to structuring displaying long-range order that is measurable and quantifiable. All metals, many ceramics, some polymers exhibit this high bond energy or more closely packed structure. You have, say, for example, here, a buckable crystal structure of carbon 60. Amorphous materials like your glass and butter have less densely packed lower bond energy structures, and this can also be found in in metals, and are observed in ceramic glass and many plastics. So amorphous materials are materials that lacking the long-range order. Now, this is just to give you an overview. Under your crystal structures, you have your crystal lattices. This is the next simplest multi-atom structure to consider for your crystalline materials. Crystal lattice is a repeating pattern of mathematical points, like in this figure here, which shows some common types of lattices. These are simple because of their repeating structures, although actual crystals have imperfections that can strongly influence their bulk behavior. Ionic or covalent bonds can occur in crystals, which are called either ionic or covalent crystals. An example of an ionic crystal is your salt. Examples of covalent crystals are carbon, silicon, germanium, and tin. They have 4 electrons in their outermost shell and form tetrahedral um, hexagonal close-packed bonds. These are some of your crystal lattices. You have your simple cubic, your face-centered cubic, your body-centered cubic, your hexagonal close-pack, and what you see here is the top view of your HCP. So if you keep repeating this order here, you create your materials. So this is the basic unit of many of your crystal structures, which you can find in your crystalline materials. Now, some additional information about your crystal systems is about the unit cell. When I say the unit cell, this is the smallest repetitive volume which contains the complete lattice pattern of a crystal. Now we have 7 crystal systems of varying symmetry that are known. And these systems are built by changing the lattice parameters. You have your ABC. So this is just the length in your XYZ axis, and your alpha, beta, and gamma, which are interaxial angles. Angles between your XYZ axis. Your crystal structures are divided into groups according to unit cell geometry. You have uh, your cubic crystal system, where your A, B, C, and alpha, beta, and gamma are equal. The interaction angles are equal to 90 degrees. You also have your hexagonal with these parameters. You also have your tetragonal with these structures. Basically, the difference between your cubic and tetragonal is that one of the uh, axis is not equal to the two. We also have your rhombohedral, your orthorhombic, monoclinic, and triclinic. You'll learn more about this crystal systems when you go to um, topics like, say, for example, your material science engineering. So these are the 14 crystal Bravais lattices, which are combinations of your crystal systems. You have your simple cubic, you have your body-centered cubic, your face-centered cubic, and then your simple tetragonal, your body-centered tetragonal, and so on and so forth. Now let's talk about your energy bands. The energy band concept is introduced in the 1928, and it looks at how the outer energy levels of states in an atom vary with distance. When atoms are close enough together, the bands from one atom can join with another to permit loss of energy in closed space band energy. Some bands are filled, and some bands are empty, and in some materials, some are partially filled. These are the energy bands for your different materials, for your insulators, semiconductors, and conductors. In an insulator, there is a large gap between occupied states and a conduction band where electrons can move in a metallic state. This one here is the bond diagram of your insulator. As you can see, you have here your valence band and then your conduction band. And the reason why your insulator does not permit the flow of electricity very easily is because of this large energy gap. Imagine if you're an electrode here in the valence band, and if you want to cross over to this conduction band, it will take enough for very large energy for you to, uh, it will need you very large energy for you to be able to cross from the valence band towards the conduction band because of this very large energy gap. And a semiconductor, on the other hand, is the same band structure as an insulator, but smaller gap between the valence and conduction band. So we still have the same energy gap here, but this energy gap is smaller compared to the energy gap in your insulators. And this is the reason here why your semiconductor can be used as an insulating material or a conducting material. It just depends on how you are going to engineer your material. A conductor, on the other hand, has a partially filled conduction band. But what happens in your conductor actually is that um, there is an overlap between your conduction and then your valence band. That is why you have here, you have this partially filled conduction band, which is different from your insulator and semiconductor. So again, let's look at your semiconductors. The focus of this lesson here are actually your semiconductors. A semiconductor has an electrical resistivity that is intermediate between those of good conductors and good insulators. And again, the reason for that one is this energy gap here, which is not very large for it to become an insulator, just enough gap for your electrons to cross from the valence band towards your conduction band. Some examples of your semiconductors are your silicon and germanium. For your semiconductors, we have actually two charge carriers. We have your electrons and holes. And let's discuss this one individually. A hole is a vacancy in your semiconductor. It is a vacancy that is left behind by by an electron. let's say for example here, that was able to cross over from your valence band to your induction band. So once an electron is able to cross over from this band here towards this band here, it leaves behind a hole, which is uh, it leaves behind a hole in the valence band which behaves like a positively charged particle. But again, there is nothing here. This is just a hole. But this one behaves like a positively charged particle. The figure here shows the motion of electrons in the conduction band and holes in the valence band with an applied field. So there is already some potential difference here. And this potential difference is actually what makes your electrons able to cross from the valence band towards your conduction band. And again, once an electron is able to cross over, it leaves behind this positively charged hole. Now, Um, in your semiconductors, there is this what we call your impurities, which is very much necessary for it to become a material that can be used in your technology. Now, you put your impurities by doping, which is the deliberate addition of impurity elements in your material. And in an N-type semiconductor, which is a negative type semiconductor, the conductivity is due mostly to negative charge or electron in motion. For example, you have here your germanium, which has four valence band, uh, four valence electrons, I mean, and you can make this one as an n-type material by getting one of this germanium atoms and then replacing it with arsenic, which has five electrons, valence electrons. And since there are excess electrons here, which will not anymore bind with the neighboring germanium, this electron here becomes a donor electron, and your material becomes a negative type semiconductor, which has a fifth valence electron that does not participate in the covalent bonding and is very loosely bound. When you say an n-type semiconductor, it means that you have n-type impurities. The energy level of this fifth electron, let's say for example in the figure earlier, corresponds in the band picture to an isolated energy level lying in the gap. So you have this one here, which is about 0.01 electron volt below the bottom of the conduction band or the donor level. All group 5 elements, including your N, your AS, your antimony, and bismuth, can serve as donors in your uh, in your semiconductor to make it an N-type semiconductor. This is the energy band diagram for an N-type semiconductor at low temperature. One donor electron has been excited from the donor levels into the conduction band. And as you can see here, the energy gap or the band gap is just around 1 electron volt. And this distance here from your donor levels towards your conduction band is just around 0.01 electron volt, making your material here as an N-type semiconductor. If we have an N-type semiconductor, we also have a P-type semiconductor, which is a positively charged or positive type semiconductor. In a P-type semiconductor, the conductivity is due mostly to positive charge motion or your positively charged hole. Now let's consider again your germanium crystal, and we dope your germanium with gallium. Now gallium here has only three valence electrons, and there is this missing acceptor hole here. Now an acceptor impurity atom has only three valence electrons, so it can borrow an electron from the neighboring atom. So it can borrow from here, or it can borrow from here. The resulting hole is free to move about this crystal. And remember that your hole is positively charged, thus making um, your your germanium here as a p-type germanium. The stolen electron in your germanium crystal, for example, is bound to the gallium atom in a level called an acceptor level above 0.01 electron volt above the top of your valence band. So you have this one here. Earlier in your n-type semiconductor, your donor level is just below your conduction band. In your p-type semiconductor, the acceptor level is 0.01 electron volt above your valence band. Gallium atom, which is an acceptor, accepts an electron to complete its desire for four covalent bonds. And this is the total energy band diagram for a p-type semiconductor at low temperature. One acceptor level has accepted an electron from the valence band. Just some caution. Saying a material is p-type does not mean that the material has a positive charge. Ordinarily, it would be neutral. It means that its majority carriers of currents are positive holes, while the minority carriers are electrons. The same idea holds for an n-type semiconductor. So for an n-type semiconductor, the majority carriers are electrons, while the minority carriers are your holes. These are some semiconductor devices. You have here your integrated circuit, your LEDs, and your solar cells. Now let's talk about some of the semiconductor devices. Let's talk about your photocell. So this is how your photocell looks like. So photocell is a simple semiconductor device. Now, when a thin slab of semiconductor, let's say for example this one here, is irradiated with electromagnetic wave, which is in the form of the light, an electron in the valence band can absorb a photon and jump in the conduction band. Again, when light hits your thin slab of semiconductor, an electron in the valence band can absorb the photon and jump to the conduction band. So what happens is that the electron in the valence band uses the energy from the electromagnetic wave, which is in the form of light, in order for it to be able to be excited and jump from the valence band towards the conduction band. And if that happens, it actually creates um, a current which you can actually measure. This is an example here of your photocell. So you have here your electrodes, and then you have your gold weld contacts. This is a ceramic material, and then on top is a photoconductive material over the top surface. And then you have your wire terminals. Now, how do you actually form this kinds of materials? So you have this, what you call your p-n junction. A p-n junction is the boundary in a semiconductor between a region containing a p-type impurities and another region containing an n-type impurities. So a p-n junction is just actually your p-type semiconductor and your n-type semiconductor combined. So that's how you're going to make a p-n junction. So one here, you have your p-type material and then your n-type material. Just like say, for example, your p-type germanium and your n-type germanium combined, or you have your p-type silicon and n-type silicon combined. That creates a p-n junction. Most examples of your p-n junction are your rectifying diodes and then your LEDs. Your solar cells are also made up of your p-n junctions. Now, your p-n junctions can be connected in such a way that you have your forward bias and then your reverse bias. A forward bias means that your p-type material is connected with a positive electrode, and then your n-type material is connected in your negative electrode. If you're going to form a circuit, this one here is a positive electrode, and then this one here is your negative electrode. As you can see here from your variable electromotive force source, the positive electrode is connected to your p-type material, and then your negative electrode is connected in your n-type material. If you're going to complete the circuit and allow the current to flow, your current flows with an exponential increase in your current. It starts with a very small current and then it increases exponentially. So this is the current in your forward bias. The reverse bias, on the other hand, is when you connect your p-type material with the negative electrode and your n-type material with your positive electrode. If you're going to complete the circuit and allow current to flow, this is what is going to happen. So there is almost no current flowing in your circuit. What you see here is actually some electrons that were able to pass through. As you can see, your diodes did not follow your Ohm's law. Remember that your Ohm's law, the current versus voltage graph of your Ohm's law, is just a straight line. This one here. But as you can see, for your diodes, on the forward bias, there is this exponential increase in current, while in the forward bias, there is almost no current is flowing. The simplest model of a p-n junction behavior that predicts a current-voltage relationship is in the form of this equation here. So this graph here can actually be modeled in an equation which is given by your I is equal to your saturation current Is times your exponential, your E, which is equal to this value here, the charge per electron, times your voltage, divided by K, which is the Boltzmann's constant, and then T, which is the absolute temperature in kelvins minus 1. So this equation here can predict this graph for your current voltage relationship in your p-n junctions. Remember that in your p-type material, you have here your, just look at your acceptor level, and in your n-type material, you have your donor level. And what happens when you're going to combine your p-type material and then your n-type material is that the acceptor level and your donor level aligns, as you can see here, and this is what you call your Fermi energy. So these are actually just the band diagrams of the individual materials in the donor and acceptor level lines. This align, forming your Fermi energy. At the p side, it has an excess of negative charge and is at lower electric potential, so negatively charged electrons have high energy bands here. At the n side, it has an excess of positive charge and is at higher electric potential, so negatively charged electrons have lower band energy here. This one here is it shows the p-n junction under your forward bias conditions. So there is this flow um, in your electron hole pair, which forms your exponential increase in your current. Here is what happens in your band diagram your um, for your reverse bias condition. And as you can see, there is an increase in this line here. Okay, as compared to this one here, so there's just a small slope. Here you have a greater slope. If a p-n junction and the reverse bias is thin enough, electrons can tunnel actually from the valence band to the conduction band, and this one is a process called your Zener breakdown. So if an electron can tunnel by quantum tunneling, you actually create your Zener diodes. Now, just to give you a visualization, this is your p-type material and then your n-type material. For your p-type materials, you have your holes, and your n-type material, you have your electrons. If you're going to combine the two, what happens is that by diffusion, some of the electrons are able to cross into the p-type material, and by diffusion, some of the holes are able to cross to the n-type material. And this actually creates here what you call your space charge region or your depletion region, which is what is needed to be crossed over in your once you're going to complete a circuit. Now drift keeps them spreading from too far away. Now in the forward bias configuration, the depletion region or the space shorts region here is effectively reduced, and you have appreciable number of electrons and holes that have now sufficient energy to cross the junction. Now, since this depletion region is reduced, it will be easier for electrons and holes to exchange or to move. Your net diffusion electrons across the bar from n-type to from n-side to p-side, and net diffusion holes from p-side to n-side will be easier. For example, here you have your n-type zinc sulfide and then your p-type silicon 100. On the other hand, for your reverse bias, the depletion region is actually increased. Electrons in the material attempt to diffuse towards the p side, and holes in the p side attempt to diffuse towards the n side. However, there is a potential energy barrier, which is this space charge region here, or your depletion region, which is very large enough for electrons and holes to cross over. Now, this is the reason here, while in your current voltage graph, in the reverse bias, there's almost no current that is flowing in your um, PN junction because of this large depletion region here. So much about your PN junctions. You also have your PNP or your NPN. So it includes two PN junctions in a sandwich configuration. So PNP meaning your P-type, N-type, and P-type, or your NPN, your N-type, P-type, and N-type. In your this one here, this actually forms your transistors. And one example of your transistor is your bipolar junction transistor. In your bipolar junction transistor, there are three regions: the emitter, the base, and collector. For example, in this configuration for your PNP, one side of your P-type material is the emitter, one side is the base, or one side is the collector, and then the N-type is your base. Your hole flows from your P up to the other end of the P. We also have these field effect transistors, which is in one variation of a slab of P-type silicon. This is made with two N-type regions on top. So you have here your P-type silicon, and for example, and then your two N-type silicon, two N-type material on top, which are called your source and then your drain. A metallic conductor is fastened to each. A third electron called the gate is separated from the slab, this one here, separated from the slab, the source, and drained by insulating layer of silicon dioxide. So this is a schematic diagram of your field effect transistor. Lastly, let's have a brief talk about your integrated circuits. Your integrated circuits are made by successively depositing layers of materials and etching patterns to define current paths. We can combine the functions of several MOSFETs, capacitors, and resistors in a single square of semiconductor material that may be only a few millimeters on the side. So like this one here. So an integrated circuit combines MOSFETs, diodes, capacitors, and resistor. This one uh, thin layer of a semiconductor material here. Depending on how you're going to use your integrated circuit, is the design of your integrated circuit here.